Hello dudes, dudettes, duders, and everyone in between. This is part 1 in a multi-part series about investing in a raw video production pipeline. At the start of your filmmaking career, it's easy to get overwhelmed by the purchases that you might perceive as necessary. The better you can understand your production pipeline, the easier it will be to make wise investments. Film is a business, and I want you to have as many tools at your disposal as possible so that you can maximize the return on any investment that you make. When you're looking at cameras, you're going to be inundated with a lot of technical gobbledygook, and sometimes it can be hard to parse the marketing buzzwords from the information that will actually make a difference to your pipeline. The factors that I consider when shopping for a camera are lens mount, sensor size, codecs, and bit rates. While there are dozens of video codecs in common use, we're only going to focus on 3 for this series: H.264, ProRes, and RAW. In this video, we'll only be discussing these 3 codecs as acquisition formats, and we'll cover editing and delivery in other videos. For real, there's a lot to go over, and I don't want to be giving you fatigue straight out of the gate. If you stick with these videos though, you'll come out the other end with a better understanding of what's going on under the hood of your camera, your editing software, and your delivery formats. That will not only increase your purchasing power, but you'll also learn how to create more efficient workflows, which will save you time and money throughout your career. And as the old saying goes, a penny saved is a friend indeed. The first thing we need to cover is some vocabulary for this video. First up, what is RAW? A RAW image is one that records the data from your camera's sensor plate with less compression than ProRes or H.264. Remember that your sensor can only make quantitative judgments, not qualitative ones. All a sensor plate does is sample the photons that hit it and report that back to the camera. The sensor plate itself doesn't understand the difference between tungsten light and daylight. It doesn't understand the difference between bright light and dark light. If a lot of photons hit it, the sensor plate reports that to the camera, and then software interprets that as bright. If not so many photons are hitting the sensor, it reports that to the camera, and the software interprets that as dark. The same thing is true for color. The sensor plate doesn't know or care what proper skin tones look like or how blue the sun is in comparison to a filament bulb. All the sensor plate can do is observe and report. When shooting RAW, your camera is recording that report as the sensor delivers it without any editorializing. The cost of this is that the files will be bigger because it's recording much more data, and the benefit you receive is that you can make decisions like ISO and color balance in post-production. Larger file sizes aren't the only cost of a RAW workflow. It's also not always easy for a computer to interpret the data, as the RAW compression is usually done with proprietary codecs, and the video file can come with sidecar information containing all of the clip's metadata. This metadata often goes beyond date and time of filming and will include things like camera information, ISO, white balance settings at the time of shooting, and even things like 3D lookup tables. If you're working on a Mac, the computer knows how to interpret H.264 and ProRes files straight out of the box. It might not be able to play back Blackmagic or Redcode RAW files, meaning you might have to download the appropriate drivers so that it can correctly parse the influx of data that it's not familiar with. Side note, while most cameras shoot their own proprietary RAW formats, there are a few cameras out there that shoot an open format. The only one I've used like that is the Blackmagic 2.5K cinema camera. Never again. With an understanding of RAW, we can talk about compression. A lot of people use RAW and uncompressed interchangeably. Well, to be fair, a lot of people use RAW, uncompressed, and log interchangeably, but we'll get there. RAW video files are compressed. Arguably, all computer files are compressed. When you record your voice to tape, you've compressed it, and you have to decompress it to listen. To speak, I need lungs, a throat, thoughts, and air to carry the sound waves. Once the audio is recorded, all I need is an SD card. That's compression, however high fidelity. When you make the transition from H.264 to ProRes or RAW, the leap in quality and versatility can be so great that it feels like you're working with uncompressed information, but it is compressed to some degree. What differs is the amount and types of compression applied to the information being recorded. When compressing a still image, there are plenty of tricks you can use without visibly compromising image integrity. For example, if there are clusters of similar pixels, you can give them the same value. To see this in action, open Photoshop and load a photograph. Then save it for the web. Choose JPEG as your compression type, zoom into the image, and then move the quality slider left and right. You will easily see blocks of color appear, creating banding. That's compression, and it's possible to find a setting that reduces the file size without you being able to perceive a difference. If you're watching this video on YouTube, I imagine that there's some banding behind me right now. Et voilà, c'est la compression. This type of compression is common for stills and video. When working with stills, you're only concerned with the horizontal and vertical axes. When working with video, however, it's possible to apply these comparisons horizontally, vertically, and temporally, that is, from frame to frame. If a cluster of pixels is blue on frame 1 and that cluster is still blue on frames 2, 3, 4, 5, and so on down the line, you don't need to save new data. This is called inter-frame compression because some frames rely on others to exist. In a system like this, there are typically 3 kinds of frames: I-frames, B-frames, and P-frames. The I-frames are the keyframes, the ones that contain a full refresh on all pixel information for that frame. B and P-frames are in-betweens that reference keyframes and only save the changes. P-frames and B-frames are slightly different from each other. P-frames, or past frames, only refer to the I-frame that came directly before it. B-frames, or bidirectional frames, refer to the I-frame before it and the I-frame after it. Inter-frame compression like this works well for delivery formats, but not acquisition or editing formats. For acquisition and editing, you want to be using intra-frame compression, that is, compression that saves each frame as a unique slice of data and can be accessed without having to reference any other frames. To represent this visually, I'm going to use playing cards. Now, the data on a single playing card is much simpler than that of a frame of raw 4K video. In fact, it's simple enough that we can represent it in binary without getting confused. The simplest unit that a computer can understand is a bit, which is a clumsy portmanteau of binary digit. A bit is a switch that can be in one of 2 states, on or off. We represent on with a 1 and off with a 0. Quick note on switches. If you've ever looked at a switch, you might have noticed that one side has a circle and one side has a line. The line represents the switch in its on state and the circle represents the switch in its off state, 1s and 0s. When you see this logo on a power button, it means that you're using a button instead of a switch, and it can be either on or off depending on what you do. The logo is actually a clumsy portmanteau of on and off. It's a 1 and a 0 as a single object. Back to bits. A 1-bit piece of information can have 2 states, on or off. A 2-bit piece of information has 4 possible states, and that would look like this. A 3-bit piece of information can have 8 possible states, and so on. Each bit you introduce to a chain of information doubles the amount of information that chain can contain. Knowing that, we're ready to compress our playing cards to binary. First, let's look at the simplest value to break down, the suit of the card. A deck of playing cards has 4 suits: diamonds, hearts, clubs, and spades. We can represent these 4 suits using only 2 bits, and that would look like this. The values will take a bit more information to store. There are 13 values for each suit, ace through king, which means we'll need more than 2 bits to store all of those values. Binary is exponential, and the amount of data that you can store doubles with each added bit. Because there are only 13 values for each suit, we only need 4 bits to store all card values. 2 to the power of 4 is 16, which is more than 13, so we can save all our values and still have slots left over for other cards like the Jokers and Manufacturer's Guarantee. This breakdown could look something like this. By combining these 2 systems, we can compress any card in the deck into a 6-bit string. For this example, I have the suit information in the first 2 bits and the next 4 dedicated to the card value. Representing a single card, therefore, will take 6 bits of information, 2 for the suit and 4 for the value. In this system of compression, I can summon the mighty Queen of Hearts with the digital string 011011 as easily as the 5 of spades with 110100. Spectacular! Let's look at how this might apply to a video file. In front of me, I have 7 cards, and I'd like you to think of these cards as 7 frames in a video file. For this video file, we're using no compression. The first card has a face and value, and that means it requires 6 bits to save that information. The second is the same, requiring 6 bits, and so on down the line, meaning that 7 frames of uncompressed video would need 42 bits to save each frame. Now let's do some compression with P-frames. We still have 7 cards, but we only have iframes, or frames that save all of the data, for the 1st and 7th frames. That means that frames 2 through 6 are only going to record changes from the 1st frame instead of full new values card by card. Frame 2 contains a command to change the value, but not the suit. That means we only need 4 bits of data to generate this frame instead of the full 6. The 3rd frame is the same thing, it only takes 4 bits of data to generate, and so on down the line, totaling 32 bits necessary for this compressed video. Something you'll notice is that the result is visually identical to the uncompressed video signal. For such a simple algorithm, that's pretty good compression. We got the file size down by 25%, and the resulting file is identical to the uncompressed file. Not a bad Wiseman score for our first run out of the gate. That was because this was a sequence that lent itself well to the type of compression we were using. The thing is, we've got 2 possible quantities we could be changing from card to card. So far, we've only been changing the value, but not the suit. In this example, let's change the suit as well as the value. At the start of this frame sequence, we've got diamonds, which mean money for the art. By the end, we've got spades, which are the shields of a soldier. Our uncompressed video still takes up 42 bits. This won't change no matter what cards we're using. For our compressed video, we've still got our keyframes in the same place, but now the suit is as much a factor as the value. Let's see what happens when we only use p-frames. These frames can only look to the past as they make changes. So as we go down the line, you'll see that the suit change is a surprise and happens suddenly on frame 7. What you're seeing is called a compression artifact. The system of compression we used has created a video file that isn't identical to the original. The human eye can easily discern where the compression algorithm has failed. Obviously, this is not good, unless you're Kanye West, in which case it's the entire premise of your Welcome to Heartbreak video. One way to minimize compression artifacting is by switching frame 4 from a P frame to a B frame. Let's see what happens with that. Frame 2 can only look to frame 1 for changes, so the suit remains the same. Frame 3 can only look to frame 1 for changes, so again, the suit remains the same. Frame 4, however, refers to frame 1 and 7 to understand what's changing, and it sees that the suit change is coming, so it swaps out the diamond for the spade. Frames 5 and 6 are p-frames, so they look to frame 1 for what changes to make, and the only change is to the value. Even though it's referencing frame 1 for changes, we're only changing the value, so the suit remains the same. And now we have a smooth transition from frames 1 through 7. Our compressed file is now identical to the original file, and adding that B frame in the middle has only taken our total file size up to 34 bits, which is still much smaller than our original 42-bit uncompressed file. We compressed the file by 20%, but managed to do it without any artifacting. Not bad, eh? For the third example, we're going to absolutely destroy the compression. You'll see that every frame is absolutely unique. Indeed, they were chosen at random. We're going to use inter-frame compression with an I frame at frames 1 and 7, and with a B frame in position 4. As we generate new frames based on the iframes, you'll see that it looks nothing like the uncompressed file. We have broken the compression algorithm's brain and rendered it a quivering husk of cowardice and impotence. At this point, nothing less than 6 bits per frame will suffice in recreating our video file. You need a codec like ProRes or RAW for your acquisition format, as you simply can't build a career off of media this low quality. The video file we created here is incredibly simple. Each frame is 1 pixel by 1 pixel, and each pixel only contains 6 bits of information. When you're shooting a video file, the files are much larger, with each frame containing millions of pixels and each pixel having values for red, green, blue, and luminance. Knowing that you can compress horizontally, vertically, and over time, it becomes easy to see how 2 video files of the same resolution and frame count can be vastly different in size. H.264 is a format that can use iframes, B-frames, and P-frames. While this is useful for keeping file sizes down, it can wreak havoc at the acquisition and editing stages. To see how inter-frame encoding can break down at the acquisition stage, shoot some trees blowing in the wind or a rambling brook. Straight out of camera, you'll see tremendous compression artifacting that will be much less noticeable if you were shooting with an intra-frame codec. Those are the basics of video compression and how RAW fits into that bigger picture. We hope that you'll join us next time as we get into how these different types of compression can affect your post workflow. Deciding when to use which types of compression in your pipeline can, over the course of your career, save you hundreds of hours, even thousands depending on how large you're able to grow your business. It's easy to get excited about tech toys and gear, but I would argue that efficient pipelines, more often than not, prove to be the difference between a successful company and one that's inert. Thank you so much for suffering through this video. We're laying the foundations for smoother workflow and a deeper understanding of what your gear is doing underneath the hood. As we tighten these screws, you'll realize that minor tweaks in efficiency have ripple effects throughout your pipeline that boost expediency without compromising quality. It'll reduce the resources needed in ways that are visually imperceptible to your client base. Are you getting it? We're talking about understanding compression. Doodly bops below. Oh, and one more thing. Was this your card?